Hello everyone. Okay, this video I'm going to show you another calculation for the reaction support or support reaction. And this time is the other example from textbook. Okay, it's 4.7. And this example, why I want to show this example, because this has a distributing loaded. Okay, yeah, in this course you have to deal with this distributing load a lot. Okay, no matter what kind of problem. Okay, you will face the distribution load a lot. Okay, so for this reaction force reaction calculation, support reaction calculation, I also pick this example for demonstration. Okay, it say there's a device, mechanical device here, and they join at the pin here. Okay, they connect by this pin support. Okay, this is A is a pin support. Okay, and this device A and B here is creates called smooth support. Okay, smooth support, and smooth support we just mentioned before. Smooth support only create normal force into your rigid body. Okay, and here he in the device here he give you a distributed loaded and also has apply moment. Okay, and and so he give you this information and he tell you to calculate the horizontal and vertical component reaction at the pin support. Okay, in pin support we have the pin support only has reaction force. So yeah, so let's calculate horizontal and vertical component reaction at the pin A. Okay. For this, for the calculation problem, yeah, first of all, we have to draw a cold free body diagram. It's a free surrounding. The free body diagrams allow you to know the problem, to understand the problem, more clear. And okay, you just draw a diagram here. Not easy to draw. Okay, so this easy to draw. Okay, okay, I have join here, pin support here. Okay, and then here. Okay, okay, I think it's good. Okay, so let's start. Okay, the free body diagram is free surrounding and write down all the force acting on this body. So okay, let's start with the, okay, A is a pin support. A is a pin support. A is a pin support. So A is a pin support. So the pin support only has two reaction force, and this is a 2D problem. Okay, so A Y, and this is A X. Okay, and okay, so and here is I have the B here. It has the smooth surface. So the smooth surface will create a normal force here. So there will be a force here. Okay, and I call it okay. I call it MB. Okay, normal force at the B. And okay, and then we have the apply moment here. It said the 90 Newton times meter. Okay, Newton times meter is a unit for moment. Okay, or torque. Okay, and okay, and then what information we have? Okay, here is 1.5 meter. Here is 0.75 meter. I shouldn't drive here. I shouldn't write here. Let me see. Okay, 0.75 meter. Okay, and here. Okay, maybe here. Okay, and there's a degree information here. Say, here is 30 degree. Okay, I think all the information. Okay, all the information we have. Okay, and then finally we miss the final one. Okay, let's distribute the loaded. Okay, for distributed loaded, okay, we have to do the simplification. Okay, that's why we have to use the skill we have learned, do the simplification of this distributed loaded. Or if you don't make a simplification, this problem is very hard to solve. So you have to make a simplification of the distributed loaded. Okay, and the simplification of distributed loaded, there are only two goals. Okay, what's the resultant force? Okay, what's the resultant force? Okay, of the distributed load, and where is the distributed load? Means where is the location of the distributed load? That means what is distance here? Okay, and in the simplification for the distributed loaded, I just told the conclusion is important. Okay, the magnitude of the resultant force of distributed loaded is the area under this distribution curve. Okay, and what's the area under this distributed curve? Okay, I just draw this once again. Okay, what's the area under this distribution curve? Here is 80 and here is 1.5. Okay, what's the area of this right triangle? Okay, I think it should be easy. 80 times 1.5 divided by 2. So is 60 Newton. Okay, and the other question is, where is the distributed loaded? Okay, this is a right triangle. Okay, and the conclusion of the position of the resultant force is just right at the centroid of this area, okay, and then where is the centroid of the right triangle? Okay, and as for right triangle, you should identify the centroid of right triangle in very, very short time. Okay, you have to treat this as common sense in mechanics of materials, because it used very, very often, so you should treat this as a common sense. Okay, so the centroid right triangle, and also I show the proof, right? Okay, even if you don't know the proof, that's okay, but memorize the conclusion. Okay, the centroid right triangle, I think it's about here. Okay, and what's the distance here? What's the distance here? Okay, did you still remember that? If you don't remember, I give you a hint. It's equal this distance here is 1.5 divided by 3, so it's 0.5. Okay, that means this distance is 0.5. This distance is 0.5. So that means this here is 0.5. 0.5. Okay, so what is the question mark? The question mark is 1.0. Because the total is 1.5. So the remaining part is 1.0. Okay. Okay, so we have made a simplification of distributed loaded. Okay, FR and position of FR. And next thing, okay, after that, okay, we can solve the reaction force AX and AY. Okay, for solving the reaction force or reaction moment, okay, so everything is statics, okay, static, everything is static. Sigma F resultant force 0, total moment equal to 0. Okay, let's start with let's tell you the for X component is 0. Okay, X component 0. Okay, do we have any X component? Okay, X component of the force. Yeah, this MB has X component. Be careful. This MB has X component. Okay, this MB has X component. Okay. So where is the X component? I think I should draw this here. Here, I draw it here. Okay, yes. It's a really a drawing a problem. Okay, so here is, so that means if I make a decompose this the direction, and it's 30 degree here, so 30 degree, and yeah, what's the angle? Yeah, such part is so annoying. Here is 60. I think here is also 30 degree, I think. Okay, here is also 30 degree, right? Yeah, I think so. I think it's 30 degree. I mean, yeah, let me make sure. Okay, here, okay, here. 30. Okay, let me do the double check. Okay, so 30 here, 60. So here is also 30. Okay, yeah, 30. Okay, make sure it's 30. Okay, so be careful. Okay, this problem you have to face this problem very often in the mechanics material calculation. Okay, so these are x component. X component looks like MB, MB sine 30 degree or MB cosine 30 degree. Cosine 30 degree. Yeah, MB and cos. Sorry, sine. Yeah, sine. Oh, sorry. Sine 30 degree. Sine 30 degree. And it's point to the left. Okay, if it's point to the left, okay, point to the left, cosine, sine 30 degree. Yes, sine 30 degree, point to the left, so it's a negative sign. Okay, and x component force, okay, here we have ax, okay, we have ax in point to the right, just assume it's point to the right, okay, equal to 0. Okay, one equation, but two unknown, not solvable, okay, so we have to use other equation. Okay, y component is 0. Y component, yeah, this normal force has y component. I think it's n cosine 30 degree, okay, MB and cosine 30 degree, and it's point down, so this negative. And here A is positive, okay, and here we have force, resultant force point down, so resultant force is 60. And anything else? Okay, no. Okay, we still have got one equation, but we have two unknown. Nothing not to solve. Okay, we use the final one. Total moment is 0. Okay, the moment. I think I just use the A as a reference point. Okay, because we use A as if we use A, choose A as reference point, we don't have to calculate moment from AX, AY. I think this might makes the calculation easier. Okay. Okay, so this MB here is create a moment with respect to A and its labor arm. Yeah, the labor arm this is just the labor arm 0.75. And the force is this direction, so you'll create a counterclockwise, so it's positive. So it's MB times 0.75 and it's counterclockwise. Okay, and so the moment from these two forces, ignore it because it's acting on A point. Okay, this force acting on A point, and the force here, the resultant force here, create a moment with respect to A. Okay, and it's clockwise, so it's clockwise, so it's FR. FR is 60. Okay, times its labor arm. The reference point is here. Labor arm is 1.0. Okay. It's let's see. This is clockwise rotation, so you will have negative sign. Okay. Okay, and the final is 90 moment, 90 moment here, and it's clockwise, so it's minus 90 is equal to 0. Okay, so after this equation, okay, so we see this after all, this only have one equation and one unknown. This is solvable. Okay, so what is MB? It looks like MB is a very simple number. This is a 90, 60, so it's 150. So MB is, oh, let me check the answer. MB is, MB. MB is 200? 200? 0.75 MB equal to 150. Okay. Yeah, MB is 200. Okay, no problem. So MB is 200, so I can use the MB is 200 to get this is 200, it's 200, and use this can solve the AX. Okay, so what's the AX? AX equal to 200 times sine 30 degree. It's 100. AX is 100. Okay, AX is 100 Newton. 100 newtons. So what's the AY? Okay, 200 times cosine 30 degree. Okay, and plus 60, so 233.2. Okay, AY is 233.2 Newton. Okay, the answer is 233 Newton. Okay, let me I just take the one decimal point. Okay, so we calculate the reaction from the pin support AXAY. Okay, and this problem I just want you to know. Okay, the simplification of distributed loaded can be you must know this skill. Okay, because for such mechanical calculation, how to do the simplification of distributed loaded, this skill used very very often in the mechanics and materials calculation. Okay, so you must know this. Okay, okay, so okay, just stop the video here and see you in another video. Bye bye. Ah, oh, where else? Stop it.